Hi everyone, so today I'm going to present to you our work on self-supervised speaker verification, where the key idea is to employ a novel clustering algorithm which uses augmentation mix for each sample and self-augmented training. As a motivation for our work, as you know, getting labels for datasets can be an expensive and time-consuming process, and training with the noisy labels can also significantly impact the performance in a negative way of self-supervised models. So for that, there have been, in general, two lines of methods to mitigate label noise. We have noise-robust algorithms, which try to learn directly from noisy labels, and we have the label cleansing approaches. So these try to remove or correct those mislabeled samples. In this work, we try to improve the performance of deep clustering models, and we also try to improve the estimation of ground truth number of clusters so that we make our clustering algorithm less sensitive to the initial number of clusters. So as a summary of our contributions, in this paper we propose a general purpose clustering algorithm, which we call CAMSAT, for clustering based on augmentation mix and self-augmented training. Our proposed CAMSAT benefits from mutual information maximization based on the IMSAT clustering framework, and also we use mix of augmentations per each sample inspired from the augmix regularization method. So as per our results, CAMSAT allowed us to outperform all other clustering algorithms, and and using those pseudo labels allowed us as well to improve performance of speaker verification compared to all other state-of-the-art speaker verification baselines. So overall, the benefits of our method are better generalizability, also robustness, and especially for large-scale datasets where we have a large number of clusters. So this allows us to gain stability of clustering under a data shift. So we also performed analysis of the contribution of each component, where we show that each component is important in our framework. Regarding related work, there have been many models proposed for unsupervised clustering, such as Gaussian mixture models or agglomerative hierarchical clustering. But the problem with these is that they are not suitable for nonlinear structures of data, since they can only fit linear boundaries. So subsequently, people have also proposed methods such as spectral clustering or support vector clustering for better handling of nonlinearity of data. But the issue that remains is that they are not very scalable to large data sets. So that's why recently people have been leveraging deep neural networks, especially that they can model nonlinearity of complex data better, and also they can scale to large data sets. So such examples, we have deep embedded clustering or IMSAT, we have also deep DPM or deep generative models. So in our case, and a close work to our CAMSAT is the use of pseudo-label method or label guessing, where they try to mix augmentations so that they get better calibrated embeddings. So this is our clustering-based self-supervised speaker verification system. So as you can see, as inputs to our embedding network, we have MFCC coefficients, and as a more efficient embeddings or inputs to our clustering algorithms, we use I-vectors, since this makes things more efficient and faster to generate pseudo-labels. So once we generate the frame level representations by the encoder, we also use attention pooling so that we generate utterance level embeddings per utterance. And then we use cross entropy loss to train the whole model of the network. This is the pipeline of our proposed CAMSAT approach. So as you can see on the right, we have the IMSAT loss. In that case, we try to enforce invariance to local perturbations by using virtual adversarial training, and at the same time we try to maximize the mutual information between each data sample and its generated clustering assignments. Based on that, we try also to leverage augmentations by trying to enforce additionally invariance to data augmentation, so that we can have better embeddings. And on the left, and this is our key contribution in this work, is that we introduce symmetry with respect to augmentation. So in that case, we leverage multiple augmentations from 1 to n, and then we compute a mixture of predictions. And then we try to minimize the divergence between that mixture of predictions in each augmented prediction. So this allows us to have representations which are labeled similarly, irrespective to any transformation, and also allows us to generate more calibrated representations and improve smoothness of our model. So these are the key equations that we use. So in that case, we try to minimize them jointly. In that case, the difference between the conditional entropy and the marginal entropy constitutes the mutual information that we try to maximize. So in that case, minimizing the conditional entropy allows us to have more accurate pseudo-labels, and maximizing the marginal entropy allows us to have more diverse labels, and in that case, covering all the range of labels and avoiding degenerate solutions or collapsing into few clusters. Regarding our experiments, we use a total number of 11 deep and classical clustering algorithms which have I vectors as input. We also leverage 7 supervised metrics and 3 unsupervised metrics to assess the performance of our clustering models and baselines. And as dataset, we use the large-scale Voxelab 2 dataset. For evaluation, we use the original Voxelab 1 test set. We also use additive angular margin softmax to train our networks, and use 40-dimensional MFCCs as feature. And we use cosine similarity for final verification scoring. And as per the architecture of our CAMSAT model, we use an MLP-based architecture comprised of 2 hidden layers. For data augmentation, we use additive noise and drum impulse responses. We also use spec augment to train our speaker verification models. And for clustering, we additionally use Gaussian noise for better exploration of clustering configurations, and between 5 and 10% of input masking during clustering. As per our results, in this table we provide a comparison of performance between our proposed CAMSAT clustering algorithm and all other baselines. So what we can see is that CAMSAT outperforms all other baselines, and increasing the size of the model, and also additionally increasing the predefined number of clusters allows us to improve the performance further, achieving a high performance or improvement compared to all others. Additionally, when using those pseudo labels to subsequently train our speaker verification model, we can see that we also managed to improve the speaker verification performance by a big margin as well. Here we provide an ablation study of all the components in our CAMSAT clustering system. So what we can see is that all the components are important to improve performance, and also that there is complementarity of information between all the loss terms. Additionally, we see that our proposed augmentations that are relevant and improve performance as well, and that when you remove an L symmetry or performing a mix of predictions at the input level, we see that here that the importance of our mixers in at the logit space, and also that mix of predictions provides effective information. Additionally, what we can see is that label smoothing or dropout doesn't seem to provide the improvement in terms of performance, and that beyond 20,000 neurons for our hidden layers, performance doesn't improve that much. We see also that beyond some clustering performance, improvements in terms of speaker verification or the downstream performance becomes much more difficult, and you need considerable improvements in terms of clustering. Here we study other distance metrics as alternatives to the KL divergence. So for example, we include the study of the Wasserstein distance or squared earth movers distance, also synchronous distance or cosine distance. So what we can see is that the KL divergence provides the best performance among all the other distance metrics. Here we study the performance of our clustering models over time, including other objective losses such as the contrastive loss, info NCE, or virtual mix-up training, or also supervised contrastive loss. So what we can see is that when using CAMSAT, and thanks to the L symmetry loss, we see that the performance keeps improving over time and that it provides a regularization effect by slowing down the convergence, which shows that asymmetry allows the model to keep exploring different configurations before settling to a final configuration. As you can see, for example, with the red curve, it has converged very quickly from the beginning, but instead CAMSAT, for example, was trying to explore several clustering assignments. Additionally, we see here when analyzing the number of the discovered clusters that CAMSAT was the best in terms of estimating the ground truth number of clusters. Actually, it was the only one that estimated very well, like almost perfectly, the ground truth number of clusters, and this is thanks as well to the L symmetry. Here we provide a comparison to other state-of-the-art self-supervised speaker verification approaches which employ an ECAPA-TDNN architecture. So what we can see is that using the generated pseudo-labels from CAMSAT allows us to achieve the best speaker verification performance compared to all other baselines, including the state-of-the-art iterative clustering approach. So as a summary of our key findings, we have demonstrated the importance of mixture in the logic space and the relevance of our idea of the notion of symmetry within augmentations. Additionally, we demonstrated that mix of predictions provides effective information, especially when we train our CAMSAT with the AM softmax in a complete unsupervised way. And we have demonstrated as well that there is complementary information between all our loss terms. Additionally, we have shown that a higher predefined number of clusters when training CAMSAT leads to improved performance. We have also shown in our ablation of all the components in CAMSAT that a higher number of discovered clusters than the ground truth number tends to coincide with worse silhouette, Kalinski-Albert score, and Davis-Bordin score clustering metrics, and this leads to slightly worse speaker verification performance. We believe this is due to the generated clusters which are less compact and worse separated in that case. We have also shown that our symmetry loss is critical to recover and estimate the original ground truth number. And finally, we demonstrated that further gains can be made by simply improving the clustering models used in self-supervised systems, for example in speaker recognition in our case. And that beyond some clustering performance, the marginal improvements in terms of the final downstream speaker verification performance becomes minimal and requires much more accurate pseudo-labels. Finally, among the advantages of our proposed CAMSAT clustering method, we find that our approach is simple since we use simple and lightweight architecture. CAMSAT is a general purpose method, and so it can be applied to other problems, not just speaker clustering. We also leverage an additional complementary supervisory signal by mixing augmentations per sample, and we find that our mutual information-based approach is rigorously grounded in information theory, and so it allows us to effortlessly avoid degenerate solutions. And also by ensembling classified predictions, this improves prediction calibration and provides consistent embeddings and improves the uncertainty estimation to previously unseen data clusters, especially this is for large-scale data sets, because each time you would be discovering or encountering new clusters or new samples. So we find that CAMSAT is very suitable in this regard. And finally, our approach is very scalable since we don't depend on any large batches or negative samples or large similarity matrices. Therefore, our approach is suitable for large-scale datasets since it's robust and stable against corruptions and data shift. And finally, by introducing Gaussian noise, our approach tries to improve the exploration of different clustering configurations so that we don't settle to just suboptimal cluster assignments. As a conclusion, in this paper we propose a general purpose clustering method called CAMSAT, which is based on two principles. First, mixing predictions of augmented samples and using as well self-augmented training. CAMSAT is highly scalable, provides better generalization, and also is robust under data shift. We also showed through our experiments that we outperformed all other baselines used to cluster speaker embeddings. We also outperformed all other state-of-the-art speaker verification benchmarks. And finally, we showed that the CAMSAT recovers the number of clusters almost perfectly and is less sensitive to the predefined number of clusters. Thank you. You can find our code on our GitHub repository.